Hi everybody. Today we're going to be going over subspaces. And what I want to start out with is sort of an intuitive look at what a subspace might be. Let's say that you have an apple. Okay? I'm not going to draw these very well at all, but we're just going to call that really poorly drawn apple an apple. And let's say that you also have a lemon. And maybe you're a farmer, we say, and you can grow more apples and lemons, so let's say maybe you add some more apples, so maybe you add 2 more apples, maybe you add another lemon, whatever. And what I want to ask you is there some way that you can get a blueberry? And the answer is no. How are you going to get a blueberry out of those? Let's say you can add any more apples or lemons, or maybe you could multiply by some amount. Say you take all your apples and lemons and you multiply them by 2, and then you double the amount of apples and lemons you get. But there is no way that you can get a blueberry out of all those apples and lemons. Thereby, you have a subspace of apples and lemons, and there's no way for all these apples and lemons to end up as a blueberry. In other words, we could say that there's a vector that consists of apples and lemons. And this vector lives in a 2-dimensional space, R2. Maybe we have apples, lemons, and let's say we have a vector V. And there's no way by adding some other vector that lives in R2 here to V that you can get V to shoot off of the computer screen towards you. There's no way you could do that. No matter what you add to V, it's always going to be either shifted or scaled in some way, but it will still live in R2. Furthermore, if you were to multiply V by some scalar that's any real number, it's not going to be able to leave R2 and end up in a 3-dimensional space. It's still going to live in R2. And this is, in essence, what a subspace is. So, we commonly denote a subspace as W, and we say that W is in some vector space. We can just call it Rn. In later videos, we'll go into more of a description of abstract vector spaces, where this becomes more important. But for right now, we're just going to say W belongs to Rn. And for W to be a subspace, it must meet 3 conditions. So firstly, the 0 vector must be in W. Secondly, if we have 2 vectors, let's say U and W, which are both in W, then their sum, U plus V, must also be in W. Thirdly, if we take some scalar, we just call it C, and we scale U by C, the resulting product is also going to be an element of W. Now, why are these important and why are they true? Think about number 1 first. So, 0 is in W. Well, this is going to be automatically required if number 2 and 3 are satisfied, okay? For the most part. There's only one instance when it's not, which is if we have a set like this, okay? Very poorly drawn brackets here, but let's say we have a set like this, and what does this contain? Well, it contains nothing. It's just an empty set. This is the only case why we need 1, essentially, because as long as numbers 2 and 3 are satisfied, number 1 always is, except for this case where we have an empty set. In this case, numbers 2 and 3 are satisfied, but 0 is not in W in this case, because this is just nothing. Really, this isn't super important. We just specify it, though, because we want 0 to be in W, and we don't want an empty set because what is the point of calling an empty set a subspace? Obviously, nothing is in nothing, and nothing can do nothing. So that's why we have number 1. Numbers 2 and 3 are important from the last example, as I showed you. Basically, as number 2 and 3 ensure that the vectors can live in that subspace and cannot leave that subspace through vector addition or scalar multiplication. This was a basic just first look at subspaces. In the following videos, we're going to go over more specific examples of how to prove and how to go about using subspaces.